So today we're going to discuss about optical coherence tomography. This is something you don't want to miss in the entire lecture. The reason I will talk about this sooner. So overall, we'll discuss about also history and applications and the background. And I'm going to emphasize a concept which is called coherence, which is inside the optical coherence tomography. And the coherence concept, I have to admit, this is not an easy concept. Even for me, I think it takes years to further understand a little more because there's a very confusion between temporal and spatial coherence. And I hope today you will be able to understand way better than me. Because I struggled to understand this before. And in between, there's a partial coherence interferometry, or we call low coherence interferometry. This is exactly what describes the physical principle of optical coherence tomography and principles and how to build out OCT, how to do signal processing, I'll go over with you. And as I'm not like majoring in OCT, I borrowed a number of good slides from very good scholars from the world. So that's what I want to say here. So first, when we start to understand optical coherence tomography, we may want to compare with some other modalities and ask the question, why OCT is necessary? And what is the stance of OCT in comparison with other types of imaging modalities? So here comes a nice diagram which I borrowed. So in fact, many optical imaging techniques, we care about their resolution and penetration depth because penetration from the surface to this multiple scattering, normally the tissue is of very much of importance for us. So let's say we've known already confocal microscopy giving an excellent sub-micron resolution. By the way, the size of the bore stands for the resolution. And the penetration that we all know confocal based on the ballistic photon and due to the pinhole, you can only get down to almost one mean free path in the tissue. So that's about 100 micron ratio. So while resolution is great, you don't necessarily have more than like 100 or 200 micron thing is very hard to see. While OCT in comparison, you can see the resolution is actually poorer than confocal. So it's about order of 10 micron, which means, remember your cells, typical target cells size is about 10 micron order for its nucleus. So you won't be able to see necessarily the cell types, specific individual cells with OCT, but there are other techniques for just using high numerical aperture objective. You can make optical coherence microscopy, which can actually target having a less than 10 microns so that you can see cellular resolution. But what's very interesting here is OCT now has a penetration depth of about 1 millimeter order, which is 1 transport mean free path. So this is great in terms of optical imaging. And so you can compare with other medical imaging modalities, which you already know. So, you've heard ultrasound, one of the most popular medical imaging technology in the world. And that has, of course, very poor spatial resolution because you are using light instead of light, sound. Sound wave has a much longer wavelength and all the resolutions half of the wavelength you are using. So it's about 150 micron. But the good thing is attenuation of sound wave through our body is very much slow or lower than light. So that's why ultrasound can penetrate several centimeters. This is ideal for clinical imaging because our body is up to like tens of centimeters. So that's where ultrasound. And I have to say, OCT is the ultrasound version of the light. So you will understand why I'm telling this. compared to CT and MRI, you guys all remember these X-ray, computed tomography, and MRI can penetrate the entire body because of high energy photon of the X-ray, and MRI is utilizing magnetic field which can penetrate through our body. And of course, resolution is rather poor, but it has can see anywhere inside the body. Right, the number of this may vary from like time to time because now we have more advanced. So sorry that last minute I actually sent you the updated slides, so it's in the website, but I wanted to discuss with you, to share with you the table so that this one and OCT, CT, ultrasound, MRI, and even PET, I put some of the numbers here, image resolution and depth. And also here comes a real-time aspect. So why real-time is important? When we do structural imaging, it doesn't matter that much. However, when we are moving things into the clinic, we want to deal with the patient's movement, breathing, heart beating. So the image speed can be a very important factor. So in that regard, OCT has a real-time capability like ultrasound, while the others are, you can see MR PET is very slow, while CT is also slow, which means it's hard to get the real time. So this real-time capability is really critical to make this OCT also a very powerful technology, and which is basically coming from the innovation in this field. So that I want to go through a little bit of the history. In fact, the history is only now 2021, only about 30 years. So why I bring OCT as a major topic here is because OCT is the #1 example of how biomedical optics just spread into the world of a clinic and adopted in real translation into a non-invasive imaging of human patients, and with a huge commercial success. So I want to give you this idea because this is something you never miss by studying biomedical optics. So when does it start? So it started from MIT laboratory by Professor Jin Fujimoto, who is a president of like world biggest optical engineers conference for like decades. So he has invented 1991 in a science paper. And what happened is just readily after this publication, people realized the importance of this and started to apply it ophthalmology and invented another variant of OCT by putting like Doppler. You can actually have some glimpse of these dynamic aspects such as blood vessels. And also sooner, like speed of OCT has been greatly improved, and also the resolution will have to be greatly improved. So that allows this technology to be readily applicable. So for example, soon like endoscopy has been a perfect application with OCT because OCT uses a fiber optic. And sooner cellular imaging has been possible by using high NA objectives. So not only just a poor resolution, you could, if you want, you could make it like microscopy. So the cellular imaging is possible. And then the light source of OCT before was actually poor, like superluminescent diode. We'll get back to this. But now, remember nonlinear microscopy uses a femtosecond ultra-fast pulse laser. The pulse in space means that in spatial frequency, it contains many wavelengths. So what that means is in Fourier domain, broadband means can make a very narrow pulse, and this allows ultra high resolution OCT. So this has been like absolute development and great enhancement. So that you can actually use this for like here the Barrett's esophagus. This is at the lower of your esophagus. There is a transition which is known to be maybe a precursor of malignant esophageal cancer. So you can use it for cancer imaging, And coronary artery, you guys all know that the cardiac coronary artery, the most killer for heart attack. And this imaging has been demonstrated. And, however, I have to say this a black bold letter means the OCT original development is so-called time domain OCT. And people, like some of you asked me that why we have to study Fourier optics. Yes, seeing things in different domains can change entirely. This is a great example. That we developed a spectral domain OCT, which means thinking everything in time domain, looking at spectral domain, people realize we can improve signal to noise ratio in nerve like huge. That means you can make a very fast imaging. So that was an amazing revolution in OCT field. So that now what you can do is now high speed, not just frame image, volumetric OCT imaging invented by Professor Seokhyun Yoon, who is now at Harvard Medical School at Mass General Hospital, MGH. And then since 2010, there has been rapid commercialization. So this is for the last, I think now it's 3 decades, but OCT demonstrated rapid development from an inception. You know, the idea is very simple, in fact, to a versatile application. And why? Because it provides non-invasive, super high speed, and high resolution possible optical imaging, so that it can be useful for clinical screening or disease diagnosis. I just brought a recent review paper by Jim Fujimoto, who's an inventor. And here's one graph. I think this can illustrate the impact of this technology. You just look at this. This is the OCT system selling revenue, and this red is funding. You see, $5.2 billion a year. So this is now becoming a huge impact to the world. And virtually, when you look at into a rather big hospital, ophthalmology clinic, they all have OCT machine. Okay, so that's something I can emphasize to you. So really, this non-invasive disease diagnostics enabled by OCT at like virtually anywhere you can imagine it has been used. So for example, ophthalmology, posterior part of the eye, there's the retina. So retinal disease diagnosis, this is excellent because previously we used a fundus camera, which only sees the top surface, but the disease are not only happening at top surface. So retinal disease, this is OCT, T stands for tomography, which means it sees below the surface layer by layer. This is just great technique, non-invasive. What about dermatology? We see our eye and see the surface of the skin, but OCT can allow us to see, even look at behind, below the skin, so the skin diseases and early detection of skin cancer is possible. Not only outside of our body, in fact, cardiovascular, which is the top killer in many advanced or developed countries. Remember, the coronary artery, there has been atherosclerotic change, which means a fatty deposits, inner layer of the arterial wall, and that forms a plaque. When the plaque rupture, the patient undergo heart attack, and it's devastating, right? And that which plaque will be predisposed to rupture or not is a very much an important question. And OCT can see inside, giving a contrast, so it can be useful for vulnerable plaque detection. And of course, this one requires making this OCT probe super thin so that it can get into the blood vessel. So you can use it as a fiber optic endoscopy. So it can be used for gastroenterology and gynecology. Not only this clinical aspect, but the basic science, this non-labeling is very useful so that embryology and developmental biology has been helped by the OCT technology. Not only the structural imaging, functional aspect, as I say, this can be very, very fast technique. And functional imaging, as a blood flow can be hurt by Doppler OCT. And also, sometimes OCT is like criticized by its limited aspect of contrast, which is solely dependent on scattering. However, you can be wise enough to make the absorption of the sample, and you could utilize OCT contrast agent, which may have a spectroscopic information. And so OCT can be used for optical properties, or the tissue sample, the specific property, especially like birefringence, and that can be also a good contrast source. So we developed a polarization sensitive OCT, especially this is good for layered structure like gastrointestinal wall. If there's a cancer arises, this has been very found it useful. Also, not only that, fast imaging technique allows us to use it for real-time detection. So that can be used for guiding surgery, such as very delicate procedure, brain surgery, knee surgery. OCT has been used, and this is a excellent application. All right. So I want to give you better to start with you to share how this application look like. So first, eye. The most accessible part of our organ, which light can go deep inside, in this case, the eye. You guys know that fovea is the place right at the near the center. That's where the most rods of your retinal cell density, so that you can actually, these are the most of the time you are using it. And there's an optic disc that's where this optic nerve is going down. So there's no cone, so you cannot see. So this is a blind spot, while your brain always processes it like you don't notice it. So for the first time in 1991 and in 2001, this is 10 years after a revolution. This is the initial OCT to looking at the surface of the retina, and you can see this optic disc and the fovea, which has a little bit thin dent over here. Okay, that's a vitreous, which is like a liquid inside this vitreous humor. And so you can see some glimpse of layer, which is very important for retinal function. Look at that, in 10 years with ultra high resolution OCT, what it has shown is, look at this nullified layer, and very much detailed layers are actually being seen. So what does it mean? This means a revolution in ophthalmology to detect and diagnose a eye problem, especially retinal disease problem of the patient. So now we can have this wonderful 3D layered imaging reconstruction. You can see this fovea, and this is a optic disc. So what this means, I have a second slide for application ophthalmology. It means that by having this, you can now be able to apply for various kinds of retinal disease. Here comes an example of commercial OCT system. You can see here, there is a disease, so diabetic macular edema. So edema is a filling of the water. You can see this verge of this macula, and also of retinal detachment. So there's a gap detach of retinal detachment. And also ARMD here is age-related macular degeneration. This is actually, my mom has this macular degeneration. This can link to a blindness in the end. So this is a very devastating disease without many treatments available. In fact, there's no proper treatment, in fact. So this is a very important disease when you get your parents, your grandparents. And so subretinal fluid can be shown. And there's the intraretinal exudate. You can see it, PED. So PED stands for pigment epithelial detachment. So retina has RPE cells called the retinal pigment cells. So these detachment can be shown in OCT. And also this one, you can see like this another type of a choroidal like disease. So this it's just impossible in previous with non-invasive way of diagnosis and hopefully better treatment. What about cancer? Yes, OCT is a great technology. It can be useful for endoscopy. So you can use it for cancer. So here's some examples. So esophagus, inside you can make an endoscopy to looking at the cellular surface. Remember, the GI tract surface is squamous epithelium, you can see, and also not only esophagus, the lower gastrointestinal tract, such as colon. If it's normal, you can see a very nice columnar epithelium, which has like crypts in it. And interestingly, when there's a cancer arises, cancer is abnormal growth. So it actually disturbs the orderly traction into disordered one. So what it means is this part, as you can see, this is normal pit and there's a loss of pit. What that means is, while it may not be the most specific, it shows something is going on. In fact, it was a carcinoma. So colon cancer arising here by looking at this OCT cross-sectional imaging. Now, this is a commercialized company's image, which has a very much advanced high resolution. Not only that, you can actually see the functional OCT, which shows a dynamic information in OCT, which is coming from blood vessel. Flowing blood vessel gives this red color, contrast, so that you can actually overlay to structural and dynamic OCT as well. So here comes an example of high resolution OCT can be even compared with a H&E stain, pathology stain. So this is human pancreatic cancer biopsy, and this, this circle, this dot actually show a contrast. While OCT is just a gray color imaging, you actually look at one by one with the H&E, realizing pancreatic cancer cells can be detected. So this is a full field OCT, which shows an en-face, meaning that you are looking, while OCT sees only cross-sectional vertical, you can combine this one to look at from the top surface. So en-face imaging, I think this is OCM because it gives a microscopic resolution. So you look at see how powerful this application, and not only this in basic fundamental basic research by life science research, you could even use this one for developmental biology. For example, frog tadpole in Korean ulcheng, and you can see dorsal, the back side, ventral, frontal side, and you can see eye development and like a medulla of the brain, and looking at this G, gills, agami, and H, their heart, the developmental heart and eye intestine. So you can actually see quite many things only based on the reflectance imaging. Not only that, now there has been, humans, our clinic has a keen interest in solving cardiovascular disease. So cardiology is, of course, a great place for OCT to explore. But remember, cardiology, most of the time, we are interested in coronary artery, where a stent is put there. We use OCT for whether the stent is well attached or not. So cardiology is a huge market awaiting for new technology. And you see this left side is OCT imaging, and right side is the H&E. And it actually detects various details in this area. But then there's a previous technology called ultrasound, called IVUS, which means intravascular ultrasound. And this new technology, compare left and right, you can see way higher resolution in OCT, while ultrasound can see probably deeper into the tissue. Finally, a recent company makes this real-time rendering of human coronary artery. Can you see this nice stent placement over here? So now the technology is that there's a guide wire here, and you can actually reconstruct 3D a stent so that you can actually check whether this is like life or death issue, right? So whether the stent was put it properly, well enough, and the nearby tissues you can actually see. So 3D rendering. So that has been amazing. So how come it's possible? And we have to go back to our basics. So now I want to like one by one with you to go through some of the fundamental definitions which form the basis for OCT. So OCT, that C stands for coherence. And what's the coherence? Coherence, just the name say, this is correlation between a physical quantities of a wave or between several waves, or wave package, which is like a packet of a wave. And so coherence is a function of a property of wave that enables stationary, 정명?
Yes.
Temporally or spatially constant. What does coherence provide us? A wave phenomena.
Interference.
Excellent, yes. Yes. Interference is something like only when coherence makes it possible. So with that, we can mathematically consider cross correlation and autocorrelation. And autocorrelation is if the waves you are dealing with is the same one at different time or position. While cross correlation is the ability to predict of the second wave by knowing the value of the first wave. We'll get back to this later. But I want to intuitively try to give you an idea of what this coherence of light means. So first, there's a wave, electromagnetic wave, and you can consider this a 1, 2, 3 rays. And in time versus space, they look almost identical. So, coherence is the defined phase relationship between different waves or set. So you can see this, okay, that's very nice. But in reality, think about this coherence beam is usually made by laser. And laser in physics is gain medium and it cannot last forever. So what it means is, this is what you really get, which is we call not like perfect or partially coherent beam, which means you can see there's a missing link, okay? What it means is, to a certain extent, the phase relationship is perfect, but over time or over distance, that defined phase relationship starts to ameliorate, deteriorate. So that's partial. What about in certain condition, like this is probably most of the time, the light you're dealing with is in fact, you see there's a kink here. There's a loss over here. What that makes it is even self or within different rays, the phase relationships start to break down. So you cannot estimate one from the other. So because they are irrelevant, that we call incoherent beam. Okay, so what are these partial coherence? This is what OCT in fact is using. And if you interfere this partial coherent beam, this is what you will see. So this x-axis is about either it can be time or it can be space. So you're looking at, let's think about the time. Over time, we have a nice oscillation, which is coming from interference. But there's a phase break. What it means is from here to here, you can see a nice wavelength to wavelength. So which means you can find the phase well. However, after this phase break, this and this, now the relationship between this delta t versus phase is now less predictable. So only that like defined phase relationship with available within this packet. And that timing we call coherence time. So this is a very, very important concept, coherence time. You know, the light propagates at the speed of light, which is c. So you can multiply tc times c. That defines the distance within which coherence is available. So that length scale we call coherence length. So this is first time I'm telling you the most important concept as in coherence time and coherence length. Later you realize this coherence length defines the axial resolution of OCT, or optical sectioning capability of OCT is nothing but this coherence length, because it depends on this coherence or interference. All right, so I just want to give you a broader sense of example of light coherency. You know, the sunlight, which, you know, all the part of sun is shining, emitting light. So not necessarily different light emitters do not know each other, in fact, so that they are like electromagnetic waves you can see has all different wavelength and amplitude. So this we call incoherent light, because there are many colors, which is different wavelength, and their phases are just random, okay? While I have to admit that even sunlight has a very short coherence length, and in physics laboratory, you can actually make holography based on sunlight, which means to certain, like several micron length, this contains actually coherence, okay? However, let's think about LED. You guys know that LED has a rather, not like peak, but rather a range of wavelengths. So that we call partial coherent light. So you can depict it like this. So they look like almost similar, but over time it starts out of phase. So it's kind of coherent to the certain extent. What it means is fewer number of wavelengths are coherent, but overall, like you will lose your phase relationship. Then what about laser? So laser is known to have really typically single wavelength. So you can see the perfect wavelength and the phase relationship. So laser is really the representative coherent light. Especially if there's a single monochromatic, meaning one color laser means one wavelength and they are in phase, and that's an excellent source of coherence light. Okay, so OCT is actually using somehow partial coherence light. So typical invention of OCT was a superluminescent diode has been used. Here, I'm starting giving you a little bit of mathematical description, which can be a little difficult, but I want you to physical understanding more at this time. So let's think about partial coherence. You remember two beams with the same polarization, so we can use electromagnetic wave is originally a vector quantity of electric field, a perpendicular oscillation, but we can just take that out to scalar. So E field of 1 and 2, like interference, is the net interference intensity to your detector C, is the magnitude square. But remember, this wave e to the I kx minus omega t, that omega t is super fast, 10 to the 14th. So we are actually seeing in our detector is averaging those temporary. So I put this this notation, and then you can see here's a time average over a period longer than the fluctuation time. Because what we measure intensity is in fact time average electric energy, then you can actually compute this inside then E1 square, E2 square, and two real component to E1 and E2 complex conjugate. And here, so you can actually see more simply, just if you have two electromagnetic fields, E1 and E2, then the result is I1 plus I2 plus 2 real time of mutual coherence function, which is defined as here, this one. All right. But we love to have a normalization to make it simple. So you normalize by this intensities, multiplication and square root, and then this become a 0 to 1 quantity we call complex degree of coherence. Okay, so in the end, you can actually describe the interference of light as a intensive 1 and 2, which forms, of course, kind of a DC component. But what matters is the second term, which is real component of complex degree of coherence. Okay, so here comes more of graphical representation. As I say, coherence length and coherence time. Now I want to describe spatial and temporal coherence. This is really difficult concept, but I will try my best to you to understand because it's so confusing. So first, what is spatial coherence? The name stands for in space, one point and the other point, if they have constant or defined phase relationship, that we call spatial coherence. When we can actually observe this, a good example is Young's double slit. So there's a point light source, and through this two slit point, we call E1 and E2, then you can combine that through a lens or through a screen. You can have a mutual coherence of these two, okay? If they have relationship, this is non-zero, and that's spatial coherence. Okay, so that sounds like obvious. Okay, Young's double slit experiment is really about spatial coherence of these 2 points of slit. Okay, that's understandable. Why? Wait a second, what about temporal coherence? Now you have to go back. I'll get back to this again, but or remember, like Michelson-Morley's experiment, which last Nobel Prize in physics to disprove the presence of ether in the Earth as a medium for light movement. Okay, so here there's a source, there's a half mirror, which we call beam splitter, and it shines the beam splits into two. There's one mirror and the other mirror, they reflect back and they combine onto the detector. So we are actually interfering both E1 and E2 field, and we are looking at the mutual interference. Okay, that sounds good. What about coherence? Because of this distance difference or optical path difference makes a time delay. And that time delay, we'll see if these delays are still maintaining coherence so that we can get interference or not. So this is really about temporal coherence. I'm telling you, this is not easy, but spatial and temporal is this different. I'll describe it the other way. Correlation of light wave in 2 points in space and time. So we are discussing about correlation between and 1 point at a time, another point at another time. When we do correlation, that relation we are talking about coherence. When it becomes to different, let's say look at this one, A point and B point while the wave is propagating, then at different, while space is different, but this is really about different time points, okay? So the correlation between these two, we are discussing about temporal coherence. And while you see when the wave is moving, when you're thinking about the big laser beam and different points of the beam, the coherence, and that we call as a spatial coherence. So look at this C and D. This is about spatial coherence. So with that, I will ask you questions. Okay. First, this figure, I consider it the most well described optical coherence. So looking at this, you see this is like Gaussian beam with wavefront at different phases, red and blue color, and propagate. So this is electric field distribution. Let's say there's a lens here, you are making kind of Gaussian focus like laser beam, and this is a nice space like temporal aspect. So this is a very good coherent laser beam. So what do I mean by spatial and temporal coherence? Looking through this, you see that X or Z axis, there's a nice phase relationship. That is the laser is propagating. So this is temporal coherence. But however, looking at this part is kind of missing now. This part is a dimmer and missing. So you can't really find the phase relationship between this and this while the laser beam is propagating. So at different time points, this will be smeared. So what it means is this has a poor temporal coherence because looking at this as a propagating wave. However, perpendicular way of at one point, ups and down, you see these one are perfect, very nice relation. So that means spatially coherent light. Let's go down to the other aspects of this. Looking at this one, you see the laser propagates for the blue-red relationship is well maintained, not like this. What it means is temporally very coherent. However, looking at this tops and bottom, within one wavefront, you see this one's now smeared out, okay? That means this has a poor spatial coherence, which is within a wavefront, the phase relationship is started breaking down. Okay, so hopefully that makes sense. And let's see, Sadaf. So spatial coherence is describing the ability for 2 points in
space.
Great. Yes, we are talking about this space, x1 and x2, in the extent of a wave to interfere, okay? And so more precisely, the spatial coherence is cross correlation between 2 points within a wavefront. Let's see, Suhyun. Temporal coherence describes the correlation of waves for 2
time point.
Exactly. Time point in a given point, and a measure of average correlation between a wave with itself delayed by a certain period of time. This can be a little confusing because this one looks to us like space when it propagates, but think about you are standing up at this point. The waves are moving. So we are really comparing at different time points. That's I describe it within along this axis. So that's more temporal aspect. Okay, so temporal coherence is such an important concept that I want to give you this mathematical description. So let's think about this K spatial axis where electromagnetic wave is propagating. You think about A point and B point electric field, okay? So we are curious about their correlation of this field A and B point at the same time, but A and B are part of a propagating wave. So in fact, they are the same electric field at just differences of T, B, A. This differences in time of the coherence, because this is correlation between the same one at different time. That means temporal coherence. However, that you can convert this temporal coherence easily into spatial coherence because the light propagates at speed of the light. So now you can define coherence length as a spatial extent along the propagation direction over which the electric field is substantially correlated or has definite 정명.
Yes.
Can you guess what this is?
Mm. I don't know.
Yeah. So let's see. Not actually. Why don't you guys show your face? Somehow I cannot see your or your face. Okay. So Nat, can you guess what this is?
Sorry, I don't know, Professor.
Okay. Yeah. This means you see this point and this point. Two different points will have defined phase relationship. That's the definition of coherence, because we are talking about the phase relationship. So how can you compute or calculate coherence length? This is whenever you are dealing with interference, this is the most important concept. Coherence length is nothing but coherence time times C. And coherence time is 1 over the bandwidth. And you know that bandwidth is and describe it as a lambda, then you can actually easily compute with this, because speed of light is lambda times nu. So delta nu, you can describe it as 1 over lambda, c over lambda, and delta nu, you can calculate this. You will see this form as a formula for OCT resolution later on. So, okay, coherence time, tau c, is time for elementary wave train to pass a single point with a defined phase relationship. So now I guess, Brahano, you can see, I mean, this answer is here, so I don't need to. So coherence length is really coherence time times c. Remember, when I call coherence length, I'm not talking about spatial coherence. Coherence length is about temporal coherence, not spatial coherence. This is the most important thing you have to understand. Okay, so let me go back again. So like laser has infinity. Okay, so this is kind of laser with the 2 different time points. You can see a nice interference pattern. But on the right-hand side, now looking at this red one and green one, in the left-hand side, there's through all the time, there's a defined phase relationship. But on the right-hand side, you will now see a little weird thing. Within this packet, the phase relationship is defined within green. However, with the different 2 different packets, because the relationship with the phase is now smeared. Okay, so now I'm gonna go into a little bit more of a temporal coherence. So if a wave contains only single frequency, or we call monochromatic, then it's perfectly correlated at all times here. Okay, so let's, in this case, what is the temporal coherence time? Laxman? Hey, Laxman, can you guess? In left-hand side, what's the coherence time?
Infinite. Infinity.
Very good guess. So this is like a perfect laser has infinity of coherence time. However, the reality is not like that. Typical lasers even have a different extent. They have wave packet of waves, which naturally has a broad range of frequencies, having a shorter coherence time because the amplitude of the wave changes quickly in the right figure. Now we talk about, what about white light, like sunlight, which has a very broad range of frequency. You know that the rainbow colors of the sunlight, which is varying quickly both in amplitude and phase, because there are a bunch of different colors and different phases mixed together. In that case, it has a very, very short coherence time, just maybe 10 periods or so. So it's often called, let's see, Raham,
Yes, Professor.
can you guess what do we mean by this case?
Uh,
Good example. Okay, so is this very coherent or not, Rahana?
the
Yeah, it's not that coherent.
coherent, Professor.
So that's why we call it incoherent, right? Okay, good job. So now let's change gears a little bit. I want to describe more of a microscope point of view of different type of photons. When you, let's say, when you send a pulse light, boom, okay, through the tissue, okay, you shine not just continuous, a pulse light, like nonlinear microscopy. So there is a light source. And on the other part, you can put your detector there. But think about this fundamental nature of multiple scattering. You know, some photons are lucky enough to just pass through without hitting any scatterer, right? That we call ballistic component. And some photons have a little chance of few interaction and still go fast. What about the majority of photons which undergoes this densely packed scatterers in the tissue? So they will undergo multiple scattering and then finally reach to the detector. So imagine that you have a very fast detector, like picosecond order detectors, then what you will see. So let's say this black one, you give an instant pulse of like photon, boom. And then you get the first arriving one, ballistic component. And then these ones we call, they look like snake, so we call snake components. So that's a fewer number of photons, fewer scattering event. In fact, OCT is for this ballistic and semi-ballistic photons we are using. Diffuse component also arrives, and this one's not for OCT, not for microscopy in general. Microscopy, like OCT, like confocal, 2-photon, and wide field, all are using only ballistic components because diffuse component ruins your resolution. Okay, so that's something. So my question, which type of photons does OCT use for imaging? You're not going to use diffuse component. You're using ballistic components, but probably not just no interaction because you need to get some information from the sample. So ballistic and snake component or very much semi-ballistic photons is for your OCT imaging, just like the other type of microscopy. Here it comes. I want to bring you attention for, again, young stubbers, which you did all this calculation of free optics and you did homeworks. But when you actually do the experiment, things are not as ideal. Why? Looking at this top and bottom case, you see top and bottom, this R1 and R2, the optical path difference is way longer in top compared to bottom one. But look at some difference. Now we are gonna be more realistic that the laser light getting in has actually finite coherence length. What it means is within this length, the phase relationship is maintained, you can interfere light. Okay, so in this case, you will have a strong interference, okay, such that these two optical differences, optical path difference is less than coherence length. What if you are going farther and farther from the center? Now you start to be, the path difference is beyond the coherence length. What's going to be your output? Now, these two waves are not well-defined phase relationship. They will not interfere. You will have on average just DC component. That's the reality. So I added just a minute ago. This is the reality. You see a nice interference pattern, but as you go farther from the center, you see it gets dimmer and dimmer. What it means is you're losing your contrast because you are losing your, it's beyond the approaching coherence length. So you are now getting more out of phase. Okay, so hopefully this one makes sense to you. And because in OCT, we are actually utilizing this property of short coherence length. So the other name of OCT is low coherence interferometry. It's interferometry, but now we are not going to be working in ideal fully coherent. We are taking a low coherence as our concept. But let's go back to full coherence case, which is a famous Michelson-Morley experiment. It's 1887 to show the consistency of speed of light, and disproves the presence of ether or postulated medium for propagation of light. Our question was, hey, in the universe, the light will have some medium, but this disproved. But this is the actual photo which led to Nobel Prize. And this is the conceptual diagram. And this is schematic diagram. So you have a laser getting in. You have one fixed mirror coming back. The other light, which is split here, goes to move over mirror 2 and come back. These two waves will be interfered at the photodetector. So optical path difference is in fact L1 and L2 difference. Wait a second, why there's 2? Because there's a go there and it's back. So it's a round trip. So that's why there's 2. And there will be phase differences based on this optical path differences. And remember, your detected light is a 2 light interference. So I1 plus I2 plus 2, square root I1, I2, and then the phase differences. In this case, this one is just perfect, and you can have constructive and destructive depending on the path length difference. So that was what we learned ideally previous. You know, OCT is based on this Michelson interferometer, except you are using low coherence light. And the coherence length is really, really defining the axial resolution of OCT. So we call it optical range of low coherence. So you look at this, geometry is the same: source, beam splitter. One arm goes sample arm, the other light goes to reference arm, come back, and you measure the detector while moving the reference arm. You see a perfect interference for long coherence. However, when the source light has a short coherence length, then you will have this nice interference pattern only within this coherence length. Otherwise, you see all dimming of this interference because it's not now phase relationship is not relevant at all, not correlated at all. Beyond this correlation, beyond this coherence length, okay? So that is the optical ranging, and I want to just explain you one by one of how this low coherence interferometry works. So first, the Michelson-Morley interferometer can be easily converted into actually fiber optic. So this has been a great advantage because you can make it tiny, tiny, narrow. So here comes the light source getting sending light and splits into two. One goes to this reference arm and come back. The other goes to the sample arm and comes back. And those will be combined into detector. If the light source is fully coherent, you will have, while moving this, a nice interference pattern, okay, which is over lambda. Wait a second. What about low coherence light that has defined coherence length beyond which, if the optical path difference between this sample arm and reference arm is beyond the coherence length, you lose all the contrast and having only a DC component. So this is what you will have. However, inside these interference is based on the central wavelength of the light. Okay, while this has many wavelengths. Hey, wait a second. Now, you actually can see, hey, looking at this sample, now we are talking about optical ranging, what I mean. And when I move this, reference arm, here, there's too much of difference. When you move it down to almost close to the same distance, now you will see this interference. And goes far away, you will go far away. So wait a second, this is a good way to detect a layer, the reflection structure from the distance from the top by moving this. This is concept of temporal domain OCT. How? Because many of our samples are layered structure, which layer have different reflectivity. Looking at our sample as this one, let's say this skin surface, top surface, and this is a basal surface, and epidermis and dermis, there are different surface with reflectance. So now you're moving this reference arm, moving, you go towards here, now there's a reflection, so you have interference here. And now you move further down, you lose this one because it's beyond the coherence length, and now you are close to here, and then you have a huge interference because there's a huge reflectance here, and then you reach to here, and then forget about the other because it's not phase relevant. You only deal with this similar part here of this. Now what you see is when you sweep one time, you are actually getting signal of this, your tissue samples, one line reflectance map. This is great. This is giving you a signal for different layer with different reflectivity. So the low coherence length now provides you an excellent way of looking at tomography, which is shining light. So this whole concept we call as a coherence scaling. Let me provide you of this because when you shine the light, the yellow one has a one single backscattering, which is good. But if they undergo multiple scattering, then photon path length, there's a multiple scattered light. But in fact, we are only caring about this single backscattered photon for OCT because we are only collecting data of within the coherence length. So that automatic interference actually removes out these photons with a multiple scattered light that we call coherence scaling. So transmitted ballistic photons take shorter path, this one, yellow one, and arrive at the detector at the earlier than non-ballistic photon. So you are kind of making this time window to only see this by using this low coherence interferometer. So we call it coherence scaling, or the other, like Jungmyo.
Time gated.
Very good. In fact, we are only in the result, we are only getting information of early arriving photons from here. Okay, so we can call it time gating. So that principle of operation now you can build this one. Okay, how? Oh, let's build one because it's just Michelson interferometer with a short coherence length light source. So, for example, diode laser, superluminescent diode, SLD, you have this beam splitter, you have this laser beam using now lens to focus it down to reference mirror, and you have a sample mirror, and you have photo detector. By moving reference mirror ups and downs, when you reach the same optical path, you will get the signal. So the other term for OCT is low coherence interferometry. This is a basis, and we are using coherence scaling. And looking at this, what is the resolution to distinguish different layers? It's really depend on this packet or coherence length. So high resolution localization of the origin of the interfering beam can be used for ranging or imaging of this complex scattering samples. And this fringe signal shows only when optical path difference is less than the coherence. Sadaf?
Length.
Exactly, yes. Whenever the two path is within the coherence length, you can have interference. Otherwise, no interference. So locating the maximum fringe visibility position is the location where the internal structure of the object. So you can match one-to-one and having nice Z scanning of image. So this is how you actually implement in fiber optics. So you have broadband source, which has a not a coherence, but low coherence. With broadband source, we have a optical fiber splitter, reference arm, you have axial scan, and you have sample arm. You only see one line, so you have to move ups and downs. So that we call lateral scanning to see at least a kind of two-dimensional map of this. And what you do is by moving axial scan, your detector gives out this signal. So in fact, remember, this is nothing but ultrasound, the same. Ultrasound measures time of flight, but light is so fast, you cannot count on the time, rather you can use interference. So it's analogous to ultrasound, and just speed of sound and light is so different. You are using interferometry to measure the small time delays of scattered photon at the reflection layers. Does it make sense? Okay, so I think I discussed most of them, and I'll just go through towards the end. So how can you make a 3D imaging? Now we know that only ballistic imaging, which means we are taking ballistic light paths, okay, based on the interference of the reflected light from the tissue discontinuities, because you are depending on the reflected light, which is just lucky that because our tissue has various layers, skin structures such as skin or intestinal layers, cardiovascular blood vessel, or a layered structure. And we are based on low coherence interferometry that we are using it as a coherent gate. So this low coherence provides optical sectioning property. And this provides your axial resolution. Okay, so OCT is my calcium interferometer with a broad band, not a single wavelength, but broad band, partial coherent light source, not fully coherent. Hey, wait a second, what about transverse resolution? That depends on your numerical aperture of the objective. What's about axial resolution? As I say, it's really coherence length. That's why temporal coherence is such important here. I'm not talking about spatial coherence, okay? And depth is about 1 to 2 millimeters. Skin is so scattering, it's 1 millimeter. Spatial resolution is rather poor, about 1 to 15. One is using like ultra fast, very broad light source. What are the contrasts in the end? It's just backscattered light, okay? And you can use some polarization sensitive, which means different polarization. You know, perpendicular polarization will not interfere. So you can decompose different polarization and you can make it as a contrast. So that's the thing. And now let's build an image with OCT. Because right now what I explained to you is only axial scan, one line, and you get this signal, backscattered intensity along this. Hey, that's one line. Okay, that's a scan, but I want to have this 2D image. Then you just scan on the side, either sample or your beam. Then you have this nice cross-sectional image. So that's a B scan. Hey, what about 3D? One line, and you sweep one line to make 2D, and then you have like the perpendicular scanning, layer by layer. So that's cross-sectional, and we call it as a volume C-scan. So you will read a lot of A scan speed, B scan, and this is what you have, 3D volume, that's a C scan. And once you have this reconstruction, you can actually look into from the top, and fast imaging reconstruction is possible. This one describes you. And I have this slide for how this is different from confocal microscopy and OCT. Confocal confocal gets optical section based on the pinhole to reject out of focus. OCT do not need a pinhole, but OCT uses low coherence length to get this optical sectioning based on the interference. Now, I don't have time to describe all different kinds, but what I describe is so-called time domain OCT. But I will say there exists Fourier domain, like Fourier optics, and that makes the speed of OCT like orders of magnitude. You don't have to get deep into here at this time, but just remember this spectral domain or swept source Fourier domain OCT makes no mechanical movement, so that it makes it like order of magnitude faster, and it revolutionized our ophthalmology. So here's like principles of that. And also getting ultra high resolution, you need a very short coherence length, you need a super broad wavelength. So with that, you can have even 1.5 micron axial resolution, which is almost like microscopy. So this slide show, hey, wait a second, I want to have a high lateral resolution. Okay, you can get lateral resolution by having high NA objective, but at the cost of the B, like depth of field will be shorter. So you have to scan ups and downs for this case compared to typical OCT. So you have always a trade-off, and this one shows this high, low NA usage of OCT versus OCM, optical coherence microscopy. And how to implement OCT. And this is a reference I just give you. The oscillation here is not your keen interest. So by signal processing, you get only the envelope, and that's your OCT signal. And this is how actually do this specifically for those who are actually developers of microscopy. And now what happens? You can actually make it as a catheter because it's based on fiber interferometry. You can make it real, tiny, and then how about hollow? You can make it hollow. This helical scanning to make a 3D of tubular organs such as esophagus and carotid artery. So in the end, I think this one I will move on. I'm going to summarize this OCT. We have longitudinal or axial resolution is based on coherence gate. That's just about coherence length. And you can see the definition and resolution of here. In terms of lateral resolution, this depends on focusing optics, similar to confocal microscopy. And interestingly, lateral resolution is decoupled or independent of axial resolution, which is only based on coherence length. All right, so that's all. And I hope this one gives you a good understanding of OCT, rather fast, but I hope you grasp the key idea. So with this, I'll give you, like, once you write down your question, I think I'm gonna finish this. Okay, thank you for your attention.